Got a metal plate here. Matter of fact, I've got a whole stack of metal plates, small metal plates. Let's assume they're at room temperature, about 70 degrees Fahrenheit. And let's assume that this is a surface that's held at a constant 125 degrees Fahrenheit. Set this on here. What's going to happen to the temperatures of the individual plates? There are about, 15 of the things, okay? If I leave this on here for a long time and measure the temperature at each plate, which I can do quickly with an infrared temperature detector, okay? Take the plates off one at a time. What's going to happen to the temperatures from here to here? What would the graph look like? Now, that can be a little mysterious. They have an intuitive sense of what's going to go on. And in the first few introductory problem sets on thermal conductivity and thermal energy, you're going to get some ideas about what might be going on here. So you want to relate what we do in those problems and what those problems are asking you to do to what we have here. Okay. Another situation is related to some of the other problems that are assigned like ones. Okay, I've got some water in this container. Water has some potential energy relative to, say, the bottom of the container, or even say relative to this tube that I've got my finger over, that water is going to flow out of when I take my finger off the tube. Okay, well, I take my finger off the tube and sure enough, water flows out. And you can see pretty quickly that it's flowing down more slowly because it's dropping at a constant rate. And it's not going as far. Okay, the parabola is changing its shape in a way that indicates that the outflow velocity is decreasing in a way that you ought to really understand, but that's not the point here. The point here is that we had a potential energy decrease, and the water as it exited had a kinetic energy. Okay. Now, if you take the total kinetic energy of the water as it exits, not after it exits and falls to the floor where it's going to gain kinetic energy due to the loss of potential energy to gravity. If I could throw the switch I have on the wall there that turns off all dissipative forces, then we would have a perfect potential energy to kinetic energy conversion between here and here. And then, of course, between here and the floor, because air resistance is a dissipative force, and so forth. Well, you don't have to worry too much about that. I want to confine it to fluid. So there was a loss of potential energy. The fluid was here, now it's here. Clearly less potential energy relative to the position of the tube. And take all the kinetic energy of the outflowing water, add it up. That should equal change in the potential energy. Now, when we do this in lab, we'll see that maybe about 80% of the potential energy changes to kinetic or something like that. And it depends on the diameter of that hole and stuff you don't have to worry about for Wednesday. Okay. Now, let's say we take this sealed Mountain Dew and put it on this presumably 125 degree plate and leave it there for a while. What's going to happen inside the container? Well, assuming the container was originally at room temperature, it's fairly obvious that the temperature in here is going to go up at least a little bit. So what are you going to do about that? What else changes inside the container? Now, you have some problems that ask about similar situations, and the key is your friend PV equals LRT, which I sincerely hope, since I think everybody has had a chemistry course, that you're pretty well familiar with. Now, of course, you can't read that because the camera doesn't like to stay in focus, but let's, come on. Okay. So we've got PV equals nRT, and that's relevant to the question we just asked. You might think about that. And my point here is that the problems I've assigned, the transition problems I've assigned for you to become very familiar with, are closely related to the three things that I've shown you here. Okay. There's also another version of this that you might as well think about right now because it's coming up very quickly. We also have PV equals capital N KT, lowercase n here with a capital R, uppercase n with a lowercase k. Okay, what is n? Well, you should know this. This is something you should never forget if you've had a chemistry course, but you should know that that's the number of moles of a gas. And the capital N is the number of particles. Okay. Now, capital R is your gas constant. Capital N times K has to equal little n times R, since PV and T are the same in both equations. So we can just note that N R equals KT. And then the question that I'll pose for you to think about is, I'm just in the habit of writing PV equals nRT, and that made no sense. First mistake of the semester, okay. Little nr has to equal big N times little k. Now, what's the relationship between little n and big N? If you know how these two are related, the number of moles and the number of particles, then you know how R and K are related. And you want to think that through as thoroughly as you can.